presenter will be Raihan. He attends Bard College Early High School and has been involved in the Harlem Children's Society program since 2007. And so please welcome him to the stage. Despite an injury today, he still traveled here to present. So I ask for your utmost respect and attention. Welcome, Raihan.
Hi, my name is Raihan. These last 2 summers, I've worked with Professor Dre and Professor Francisconi at their labs, their chemistry lab here, and we worked with Zr-Porphyrins and Polyoxometalates. Right. So, as you probably may or may not know, hopefully you do know, that global warming is a serious issue right now, and we need to be able to do something about it. And the only thing we can do is come up with a new source of energy that doesn't release greenhouse gases and pollute the air. So, and this new source of energy, people have been thinking that it's rocket science, but it's really not, because this new source of energy has been there for 4.6 billion years, and it's been powering our solar system for all of that time. So, and we'll do so for another 4 billion years, and that's the sun. And so the question is, why are we using this? And the reason being is that the technologies that are out there right now are very expensive to get, and that is the reason why we don't use solar cells as often as we like to. So my mentors and I thought about making a new type of material that would replace those expensive solar cells and basically promote people to use solar cells more often. So we started thinking about porphyrins. Porphyrin is a compound that I'm going to talk about later, and we started using a porphyrin and hafnium metal. And this project started a year before I joined them. So they started working with the porphyrin and the hafnium metal, and they put the porphyrin. This is the porphyrin, and this dot is metal. And they put the porphyrin onto the metal, and then that complex was pasted onto a TiO2 plate like this, and supposedly sunlight is supposed to hit this, induce a electric current which passes through the metal onto the TiO2 plate, which acts like a semiconductor. And what they found out while doing this project was that it actually works, but there was a problem. And the problem was that the porphyrins were attaching more to the defect sites than to the normal sites. What I mean by that is that TiO2 plate has defect sites like this, where it's jagged and not flat, and then they have normal sites like these. And these porphyrins were attaching to the defect sites a lot more than the normal sites, and that was a problem, because we want something that attaches to everything, not just defects or not just normals. So when I joined them, I started working with zirconium porphyrins. Zirconium is another metal. It's slightly smaller than hafnium, and it's a lot more abundant. And because it's a lot more abundant, it's going to be a lot more cheaper. And since porphyrin is almost everywhere, the whole thing should be cheaper and should work. So you guys are probably wondering what porphyrins are. Porphyrins are basically organic complexes that are found all over nature. They're found in your blood, they're found in your vitamins, and even in plants. So plants use a porphyrin. They use a metal-based porphyrin that collects sunlight and transfers it to energy, and that's basically what we're doing. And there's millions of different types of porphyrins. This is the porphyrin found in your blood. It's the iron-based porphyrin, and the most simplest form of porphyrin, and it has a special name, and it's called a porphine, and it looks like this. and once you add all this crazy stuff to it, they become porphyrin. When I work with two types of porphyrins. I work with the tetraphenylporphyrin and the tetrapyroporphyrin. The tetraphenylporphyrin compared to the tetrapyroporphyrin is a lot less stable, which is better because since it's a lot less stable, it's easier to change accordingly, change it the way we want it to. So we know for a fact, and that is, I guess you can call it our hypothesis, that it's going to be harder to work with the TPYP, that's the tetrapyroporphyrin, than it will be for the tetrapyroporphyrin. If you remember, there was a big word on my title screen. It's polyoxometalate, short for POMS, and these are basically metal oxygen clusters, and they're formed under acidic conditions. So all these are just a bunch of metals with a lot of oxygen clustered together, and they serve various purposes, and there's hundreds and thousands of different types of these all over the place. The reason we use it is because they mimic oxide surfaces. So when you paste a porphyrin onto TiO2 surface, you can't do much testing on it. The most you can do is some fluorescence spectrum, and that's about it. You don't know how exactly the porphyrin bonded onto the TiO2 surface. But when you work with polyoxometalates, they behave just like that, but you can do a lot more testing. And the reason we use it is because it's very easy to change it, just like porphyrins is very easy to change around. So this is a polyoxometalate called the Kagan, and it's also known as PW12 because it has one phosphorus, that's the yellow, and 12 tungstens, those are the metals, those are the blue ones, and a lot of oxygen. And all I had to do was add some TBA salts to it and change it to PW11. And this part right here, or this part right here, acts just like the surface of a TiO2 plate. So, for my project, we first have to take the TPP, that's the less stable porphyrin, and put metal inside of it. So it looks like this. So I was working with zirconium, so this is going to be a zirconium TPP complex. And once I have that, of course you analyze it, and then you put it. So this is a 3D figure of that zirconium porphyrin. So porphyrins look flat with 4 sides, and this is the metal here. After you analyze that, you paste it onto the palm, and you get ternary complexes like these, which we analyze again to see the structural properties, and based on that we can tell how well it's going to bond to the TiO2 plate. So after doing all that, you actually do paste it onto the TiO2. So you take this porphyrin, metal-based porphyrin, and you actually paste it onto the TiO2 plate. And last year we sent this to Johns Hopkins because they have more equipment to test this than we do. And after all of that is done, we do this whole procedure again with the TPYP. And like I said earlier, it's going to be a lot more harder to work with because it's a lot sturdier, it's a lot stronger, it's harder to change. So, results. When I first combined zirconium with the TPP, it was hard for me because I was new, and it took me about like 2 to 3 hours. But after getting that done, after doing it several times, we can successfully make a zirconium TPP complex, and it's not that hard. This is what it looks like when it's in a solution. It's reddish, purplish color.